So for the peroxy acid reaction, we looked at SYN addition to the cis isomer of the alkene. Now we're going to look at SYN addition to the trans isomer of an alkene. So SYN addition to a trans isomer will create the trans enantiomers, and the difference would be that instead of having where we had previously defined the configuration of the cis as RS, we now have RR for these specific enantiomers. Now, this will not always, I cannot promise that this would always be the case, that all trans enantiomers are going to be RRSS. You would have to go through and figure out the configuration of each stereocenter on your own, unless you have a similar molecule, a stereoisomer on a previous page that you've already defined. So because I've already defined the stereoisomers for the cis isomers, then the diastereomers of the trans isomers, I can easily identify the configuration of the carbons. Okay. What if the two substituents are the same for a cis isomer? Well, SYN addition to a cis isomer that has identical substituents on the alkene will produce a meso compound. So we have two stereocenters, but there is an internal mirror plane of symmetry. And that means that it has a superimposable mirror image, and that it does not have an enantiomer. All right, looking at stereochemistry of the hydroboration-oxidation reaction. I mentioned previously that the boron and the hydrogen add at the same time. So we're forming two new bonds at the same time, and that means it can only occur by SYN addition. Anytime you form two bonds simultaneously on a molecule, and both of the atoms being added come from one molecule, then it only occurs by SYN addition. So if we start with the cis alkene, we will always have the, well, we can't say that. No. We'll look at some different examples. We will always have SYN addition of the H and the B, and so you should always make sure that they are that the H and the hydrogen added and the hydroxyl added are on the same bond type. Okay, so for example, I have this cis 1,2-dimethylcyclohexene, and hydrogen and OH add on the same bond type. So the methyl groups remain in the same bond type. But because the hydrogen and the hydroxyl group can add either above or below the double bond, when they add below, they're both on the hatched wedge. And when they add above, hydrogen and OH will be on both solid wedge. And so we have a pair of enantiomers. And if we define the stereochemistry of the enantiomers, and we're not going to create a set of 4 diastereomers, because if we only have SYN addition, then we'll only create a pair of enantiomers. If we have both SYN and anti-addition, then we can create all 4 diastereomers. But since this is only SYN addition, we can only create one. All right, so hydroxyl is group 1 for this carbon. We have 1 is OH, 2 is the C hatched CH3, H solid wedge to the rest of the ring. Then 3 is the CH2 at the clockwise from the counterclockwise from the stereocenter circled. The first CH2 group counterclockwise from that direction. And then 4 is the methyl group, CH3. And the reason that 3 is the CH2 group is because it actually is several CH2 groups. It keeps going in a chain. So if I draw my things, I would have 1, 2, 3, and I am going clockwise. So this stereocenter is R. That means that over here it is S because it will be the opposite. When we switch hydroxyl from being solid to hatched, it will be the opposite, so it's S. And then on this side, this is when this stereocenter, let's use a different color, circled in blue. When we identify that stereocenter, I choose it because the hydrogen is on the hatched wedge. Carbon 1 is the S asymmetric center. Carbon 2 is the ring carbon on the other side. And carbon 3 is the methyl group. And group 4 is the hydrogen. So going this way, we are going counterclockwise, going from 1 to 2 to 3, because we go from about 5 o'clock to about 9 o'clock. So the blue stereocenter then is R, and then on the other side it would be S. So we can, in that way, define completely what our two asymmetric centers stereochemistry is, and that is good practice. So our two, in this case, the two configurations of the product that we get are RS and SR, and these are enantiomers, and we can also write the products as mirror images. So then what would be the name of the molecule if I wrote it out, the complete and full name? So for this one, we would have 1S, 2R, 1,2-dimethyl, cyclohexanol, CLOHEXANOL, which would mean that the difference for this ring would be that it would be 1R2S, and then the rest of the name would be the same. And then it would be 1,2-dimethyl cyclohexanol. So that's for the hydroboration addition to a SYN ring. Another example, when we only have one substituent on the pi bond instead of two, we still create a pair of enantiomers, but instead of and we still have two asymmetric centers. So anytime that I do a hydroboration reaction, even though we're not required to draw the hydrogen, I sometimes draw it anyways so that I remember that if the hydrogen is adding on the same wedge type as the OH group, any other carbon bonded at the same carbon as the hydrogen has to be hatched. And if I draw a hatched hydrogen with a hatched hydroxyl group, then at least one other group on the hydrogen carbon has to be solid. So just it helps you to draw the correct enantiomers for hydroboration to draw in the SYN added hydrogen. Okay, stereochemistry of reactions that form a cyclic bromonium ion. When we have reactions where we are using Br2 or Cl2 as a reagent and we go through a halonium ion intermediate, the products of these reactions, whether we have CH2Cl2 as a solvent, which is inert and just gives us the dihalide, whether we have, whether the solvent is water or methanol, for example, and this produces the halohydrin. Water produces the halohydrin, which has one halogen group and one hydroxyl group, and the methanol produces haloether with one halogen group and one ether group. The two groups added will always add anti. So it only produces the trans, basically, provided that both of the two groups added are the priority groups at the respective carbons. So in this case, the dihalide, we would be adding one halogen on a solid wedge and one halogen on a hatched wedge. For the halohydrin, you would be adding a halogen, for example, on a hatched wedge, while you added on a solid wedge, and then the hydroxyl group would have to be on a hatched wedge, so that they're adding on different wedge types. They do not ever add on the same wedge type. But notice that if I have solid on one side and hatched on the other, I can also produce its isomer where the X is on the hatched and the hydroxyl is on the solid. But I don't have room to draw that here. And the haloether would happen in much the same way. If I added, for example, X on a hatched wedge, then the ether group would add on a solid wedge and be anti to the halogen. Okay, and we would also create its enantiomer with X on the solid wedge and the ether group on the hatched wedge. So looking at the halonium ion, we can only have anti-addition because when we add the bromine to create the halonium ion, that bromine is forming two bonds simultaneously, so it can only add SYN. If the bromine is attached in SYN, then when the nucleophile attacks, it can only create anti-addition because the wedge type that would result in SYN addition is not available. It's already occupied. So the halogen initially adds SYN, and then the nucleophile, whether it's bromide, water, or methanol, is going to add anti to that halogen that formed the halonium ion. So we can look at examples of this reaction. Laser pointer. If we have a cis alkene and we do the dihalogenation of an alkene with completely unreactive anhydrous solvent, not participating in the reaction of dichloromethane, what we get is that one bromine adds up, the other bromine adds down. They add anti, and when you draw the Fisher projections, you should draw the bromines on opposite sides. That's if you start with a cis alkene. If you start with a trans alkene, we are still drawing the bromines on the opposite sides, but you have to maintain the original trans configuration of the group. So notice the hydrogens are on different group types, they're trans. The methyl and the ethyl on different group types, they're still trans to each other. But what that results in when you draw the Fisher projection is that both of the halogen atoms end up on the same side of the Fisher projection. If the substituents are the same and we have a trans, then when we will end up with anti-addition to trans results in a meso compound. Anti-addition to trans with both sp2 carbons having same groups makes meso. Now you can figure that out for yourself. I believe that you would be able to draw the products without memorizing that anti-addition gives you, anti-addition to trans results in meso. But if you wanted to memorize it, it would be one less thing that you had to think about when you were answering questions on an exam. All right, how about anti-addition to rings? This is probably a more favored question to ask. They like to ask questions about adding Br2 to a cyclic alkene. And it's actually a much easier question to answer because if we have a simple cyclic alkene with an unsubstituted, with the ring pi carbons not having any branches, then the products will be the trans stereoisomers of the ring with the bromines on different wedge types indicating anti, the anti-products. Because we know we have anti-addition. So one of the things that some students like to remember, this is just a short thing to help you, that if you have cis with anti-addition, that's okay. And you can have cis anti, you can change one of the terms, but you can't change two. So for example, you can have cis and anti, and that's okay. You can have trans and anti, and that's okay. And you can have, but you can't have cis, anti, and erythro. You can have cis, anti, and cis, but you can't have, and your book will explain this way better than I can. I don't recommend this slide. For me, it doesn't make sense. So cis and anti create either the Threo or the trans product. Trans and anti create either the erythro or the cis product. But the cis and anti do not create erythro or cis product. I believe that's how the slide is read. For me, that does not help. I have to physically draw the products. And that's what I recommend for you. Keep paper next to you and draw out the products, okay? So this is a table of summaries of the different types of addition and what stereoisomers will be formed. So in general, addition reactions that create one asymmetric center in the product. If the reactant does not have an asymmetric center, then the product will be an asymmetric, a racemic mixture. So if the reactant has no asymmetric center and we create a new asymmetric center in the product, then we create a racemic mixture or a pair of enantiomers as our product. An enantiomer product. Pair of enantiomers for your product. That's what racemic mixture means. Approximately equal amount of enantiomers. If the reactant has an asymmetric center, then the addition of an asymmetric center results in diastereomers as products. Because the asymmetric center of the reactant will never change. That means all products will have one stereocenter the same, which is the definition of a diastereomer. Addition reactions that create two asymmetric centers in the products. Here are the possible outcomes. The addition of reagents that form a carbocation intermediate. In this case, for when we create the two new asymmetric centers, we can have both syn and anti-addition to both asymmetric centers, and that results in 4 stereoisomers formed. Both cis and both trans isomers of the products. For the addition of H2, creating 2 new asymmetric centers, we can only have syn addition, and that will affect then you will only make a pair of enantiomers in the product. For the addition of a peroxy acid, we have syn addition to a double bond. If we start with a cis double bond, then we get the cis enantiomers. If we start with a trans double bond, we get the trans enantiomers. For hydroboration, again, we have syn addition. So if you start with a cis double bond, you get cis enantiomers. If you start with a trans double bond, you get trans enantiomers. For a cyclic molecule. And then for the addition of Br2 plus H2O, or Br2 with an alcohol, then the 2 groups that add, the electrophile and the nucleophile that add across the pi bond, will add anti to one another. That means if you start with a cis double bond, you get trans enantiomers, and if you start with a trans double bond, you will get cis enantiomers. Then we have the summary of compounds that can be formed from an alkene. Notice that all of the reactions we went over in this chapter are here. If we start with this alkene, and we treat with H2PDC, we get the alkane. If we start with Br2 and we treat the alkene with Br2, we get a dihalide. If we start with the alkene and we treat with HBr, we get 1 bromine added. If we start with the alkene and we do acid catalyzed hydration, we add an alcohol. If we start with the alkene and we do hydroboration-oxidation, we get an alcohol. If we start with the alkene and we do acid catalyzed alcoholation, we get an ether. If we do ozonolysis of the ring, then we get this dialdehyde. If we do a peroxy acid reaction with the alkene, we get the epoxide, and so on and so forth. We even have that if you start with the alkene and you do Br2 and H2O, you get the halohydrin. So this is a really good summary. I like to call it a reaction explosion diagram, where you start with one type of reactant and you show everything that you can do with that reactant. And that is the end of chapter 6.